Hello, everyone. We are Team 18, Team Latitude of the NASA Lucy Student Pipeline Accelerator and Competency Enabler. We are a collaboration between Purdue University, George Washington University, and Rutgers University, and today we'll be presenting our PDR on the Insomnia lander. Before we go into the details, I'd like to first introduce my team. Working in the project management role, you have myself and Anna as the Deputy Project Manager. On the engineering team, we have Tony as our team lead, along with myself, Anna, Zoe, and Jane. On the science team, we have Anna as our team lead, along with Hadir and Minnie. Wrapping everything together, we have Hadir as our business team lead, with Tony assisting that team.
To give a little background, Enceladus is the sixth largest moon of Saturn and is located in the E ring. It's considered an ocean world that is about 500 kilometers in diameter. In 2005, NASA's Cassini spacecraft discovered the icy water particles and gas gushing from the moon's surface at approximately 800 miles per hour, coming from linear depressions known as tiger stripes in the South Polar region. The Insomnia lander has three main scientific objectives, including investigating the conditions of the plumes and fallen matter, including chemical, physical, and biological conditions, investigating interactions of Enceladus with its surroundings and its effects on the tidal forces and recreation of Enceladus's surface, and finally establishing the characteristics of life and mapping Enceladus's surface for future mission landing sites. The Insomnia lander is equipped with three optical instruments, including THEMIS, Mastcam-Z, and LiDAR. THEMIS is a thermal emission imaging system that will be utilized for thermal imaging on this mission. Mastcam-Z will be used as its dual camera heads to capture high-definition video, panoramic color, and three-dimensional images with zoom capabilities to assist in topological modeling. And LiDAR is the final instrument and is a light detection and ranging system that is used using laser pulses to obtain distance measurements that will assist in the descent profile adjustments.
The two sampling instruments we will be using are the Ptolemy and the Selfie. The Ptolemy is a gas chromatograph and isotope ratio mass spectrometer. It determines the chemical and stable light isotopic composition of the surface. The Ptolemy sample heater subsystem heats, purifies, and identifies gases released from the samples. The ion trap mass spectrometer obtains the stable isotopes of the elements. The Selfie, or the sub-millimeter Enceladus Life Fundamentals Instrument, observes molecular species important to life in the formation of water and habitability. The overall goal of the Selfie is to determine the chemical composition of Enceladus's interior ocean, the abundance of the chemicals found in the plumes, and detect traces of water and gases coming from the surface of Enceladus. The data from the Ptolemy and the Enceladus will be used to determine whether or not life exists on Enceladus. The data below, shown below, is what is expected of Selfie, but the data itself is not from Selfie.
The structure of the lander will provide support to the mission hardware and secure them to the inside of the lander. It will facilitate during the landing on Enceladus, providing more control than the instruments by themselves. The overall geometry of the structure without the legs and the hardware is a radius of 25.1 centimeters and a height of 70.2 centimeters. This will yield an inner radius of 25 centimeters and a height of 70 centimeters to provide enough volume for the hardware inside of the structure. The hardware needed for the structure includes aluminum 6061-T6 sheet metal with the desired thickness, landing legs to stabilize Insomnia on Enceladus, support beams inside the structure to secure hardware to a fixed position, and a molding piece for the CNC machine to shape the cylinder shaft. As for the validation of the structure hardware, the team will run various tests including bending and torsional stress tests, assemble burn and vibration tests, and temperature tests to simulate mission conditions that the lander structure will experience. The lander structure is validated if the lander integrity will be stable with no disconnections of the welding points, fractures, or cavities on the surface of the structure. The validation of the structure design is further confirmed by completing bending and tensile stress calculations. If the mission were to be successful with no failure modes encountered, the maximum force encountered by the structure is 45 newtons with a factor of safety of 1.5. This force induces the following bending and tensile stresses. This is considerably less than the ultimate tensile stress of 414 megapascals, which proves the lander will remain structurally sound.
In order to descend onto the surface of Enceladus, 5 Cyclone 4 thrusters will be used. 1 main thruster is located at the bottom of the lander, and 4 used for attitude and control. About 6.5 kilograms of fuel will be required to land on the surface. We selected the Damascus sulcus tiger stripe due to its proximity to points of interest like plumes and its relatively flat topology. In order to descend onto the surface, a dual burn descent will be utilized to save on delta V. The first burn will burn at apogee due to its higher efficiency, and the second burn will begin about 10 minutes before touchdown and burn until touchdown. SLAM will be used to pinpoint a specific landing point within the landing zone once it maps the surface during descent.
The electronic subsystem is responsible for general functionality of all other subsystems, and automatic landing and probing system that uses extended Kalman filter SLAM algorithm. The hardware needs to be radiation resistant to function properly, so we chose a radiation-hardened Kintex Ultra Scale FPGA, which also has a radiation-hardened block RAM attached to it. And for the data storage, an SD card with 256 GB capacity will be used. To validate the hardware, a single event effect test for radiation hardness and a temperature range test can be performed, and the software can be validated by conducting tests in settings similar to Enceladus. The purpose of the communications subsystem is to transfer any data collected and an analysis to the orbiter. For hardware, we chose the EnduroSat Ultra High Frequency Antenna 3 that is deployable, lightweight, and low power. This can be validated by testing wireless communication between the lander and a satellite network in low Earth orbit. It will use software provided by EnduroSat to control the deployment of the antenna, which can be validated by ensuring that the deployment is at the right timing and that it will be activated simultaneously with the deployment of the lander.
In order to ensure the success of the mission, a state and trigger model was developed to prevent any disruptions from causing complete mission failure. The state and trigger model autonomously manages disruptions to the mission due to the distance between Enceladus and Earth. The state and trigger model defines subsystems in either a nominal, hazardous, or failed state, and disruptions are defined as causing a subsystem to go from a nominal to hazardous or hazardous to failed state. These disruptions trigger safety controls to attempt to return the subsystem to a nominal state. For example, the thermal management subsystem monitors the temperatures of all other subsystems. If the temperature reaches above 20 degrees Celsius, it is considered a disruption and thus triggers the electronic subsystem to disable any non-essential electronics and instruments on the lander. Occupational risk mitigation is also important to protect those that are manufacturing the lander. These manufacturing hazards include slips, falls, burns, and battery fires. Employees and contractors will be given significant technical and safety training to mitigate the risk of injury during development, and social distancing protocols will be strictly enforced to mitigate the impact of COVID-19 on the team.
Our mission will span over 10 years, with the first 4 years constituting of operations on the ground, along with launching the Sonia lander by 2024. The lander will reach Enceladus in 2030 and last 2 days on the moon before we conduct a decommissioning review. We have divided our schedule into 7 parts to keep track of the important tasks and dates without missing on any of the set milestones. The first year will revolve around things such as mission design, research and development, descent maneuver and landing plan, and proposing a detailed project budget. The following years will focus on things such as analyzing Enceladus and its atmosphere to choose an entry and landing site, designing the instruments, having a testing phase in which to test the lander on Earth, and thus establish testing requirements on Enceladus. The finalized budget consists of travel expenses, salaries paid to employees, which will increase over the years, that account for a total of around $3.5 million, including benefits, instrument costs, ground operations, and the research and development of new instruments that the spacecraft will be equipped with. The selfie instrument and the launch vehicle are the main components that significantly increase the budget, making it possible to reach the $340 million mark. We have a budget surplus of approximately $57.5 million, which can go towards future research purposes for other missions and STEM causes in the work and education field. The mission outreach activities will be centered around gaining awareness about STEM and our mission, and would play a crucial role when it comes to defining the purpose of our mission and garner attention and interest in our mission as well.
To briefly summarize this PDR, we have established clear scientific goals and engineered a method of achieving those goals, mainly focusing on furthering humanity's understanding of the origins of life by developing an understanding of the conditions on Enceladus which may have fostered life in the past. Next step for this project include further developing the concept based on feedback from the PDR, developing high-fidelity CAD models, and beginning the process of hardware development and manufacturing. Here are our references. Thank you for watching our presentation.